guys, welcome back. We're doing 2.3, polynomial functions of higher degree with modeling. So basically what we did with linear and quadratics, how everything moves, the transitions, translations, we are going to apply those to higher level of polynomials, and we're graphing. Okay, so I'm not going to spend a lot of time on these slides, just because hopefully we get it. We can go over it in class. If it's greater than 1, it's a stretch. If it's less than 1, or if it's between 0 and 1, it's a compression. If it's a positive, it's a positive function. If it's a negative function. The H translates it left and right, and it's always opposite of what you would think. And the K moves it up or down, and it is as it is, okay? So if we have this graphing transformations of a monomial function, and this only, this only counts for monomial functions. Whenever we get into the x squared plus, or x to the 4th plus 3x squared minus x plus 4, then we'll have to use Desmos, the graphing calculator, or we'll figure it out. But with monomials, we can use whatever degree it is, we can use our transformation rules to apply to it. So here we only have this one x, it's not plus other functions. So we can look at this 4, it's a stretch of 4. Okay, plus 1 means it moves to the left one. Okay, and it's a cubic. Okay, and so if we have x to the h, so negative is a reflection over x-axis. Okay, it moves to the right 2, and then it moves up 5. Okay, I think it said to check with a grapher, compute y-intercept, and so y-intercept, your x value is equal to 0, so we plug in a 0 for x. So if we have 4 times 0 plus 1 cubed, well 0 plus 1 is 1, 1 cubed is 1, so 4 times 1, so your y-intercept is at 0, 4. Okay, here if we plug in, we have a negative, and then 0 minus 2 to the 4th plus 5. Okay, so 0 minus 2 is a negative 2 to the 4th power, so that would be 4 times 4, which is 16, and that's a positive 16, but we have a negative, and then plus 5, so it would be negative 11. So that would be 0, negative 11 for your y-intercept there. And if we look, I think we have these graphs. So stretch of 4, left 1. Okay, your x-intercept is at 0, 4, which is right there. Here, reflection, right 2, up 5, y-intercept is at 0, negative 11. Okay, so here, graphing combinations, and so here, this is what I was talking about, this is no longer a monomial, because we have an x cubed, and then that's included with a x. So here we can't just think about how it moves left, right, up, or down. We actually are going to use a grapher, okay? And so if we graph it, it says to locate its local extrema. So local extrema is your max and min, your zeros, and explain how it's related to the monomials from which it is built. And so this is from a cubic plus a linear, and it's just spread out. And so if we find our extrema, we have max. Our maximum is right here, and so that is negative 0.58 and 0.39. Our min is 0.58 and negative 0.385 or 39. Okay, so if you look, these are reflections about the origin, and that is, your y equals x. And so those are reflections about the origin, and so that's related to the monomials from which it's built. So it's x cubed. And then it is a reflection over the origin, which is your x's and your y's are flipped. Your zeros are where it crosses the x-axis, and so that would be at negative 1. It would be at 0, and it would be at positive 1. Okay, and so we are going to, that's all we have to do here. You notice we have one maximum, we have one minimum, so we have 2 local extrema. And then we have 3 zeros, and that is based off this right here. Okay, and so let's look at, we'll go back to that. So if we have here's some cubic and some quartic functions, and so if it's positive, if it's a monomial, it would be like this, x cubed. would look like that. And then here is another cubic, but it has other polynomials attached with it. And this is a positive because it's down and then up. Okay, here are two negative cubics. So this would be the monomial cubic, it looks like that. And then this would be another negative cubic, but you also have other polynomials attached with it. Okay, and that one is from down to up. Okay, or sorry, up to down. And then if we look at quartic, so this would be x to the fourth power. Okay, and so we have, again, it's kind of like a widened out parabola. So that would be the monomial of a quartic. Okay, and here would be a positive. So if you look, it goes down, up, and then it goes down a little bit again, and then up. Okay, so if you notice here, we have 1, 2, 3 local extremas. Okay, and then you can have up to 4 zeros, which again, we'll talk about. Here would be, and so both of these, up and up, so that means it's a positive quartic. Here, B would be a negative quartic. Here would be the two negative quartics, okay, and they're both ending down and down, okay, and so there you go, negative leading coefficients. And so this theorem, a polynomial function of degree n has at most n minus 1 local extrema, and so like this one, if 4 minus 1 is 3, so you can have at most 3 at most extrema. Okay, so this one has just 1, this one has 1, 2, 3, this one has 1, and this one has 1, 2, 3. Okay, and if we go back to the cube, x cubed, this one doesn't have any, this one has 1, 2, this one doesn't have any, this has 1, 2. Okay, and then your zeros, you can have at most 3. So you can have at most 3, here you can have at most 4. You may not have, any actually. So here's the limits. This is in your Google Slides. I'm actually going to go to the next slide to talk about a little quick thing. And you guys can't even read this on the YouTubes. So we're going to go to this one. And so if you have for leading coefficient in the test determines the end behavior. And so these are represented as limits. And so it says the limit as x approaches infinity. And so remember, positive infinity here, negative infinity is here. And so we're looking at the end behavior. And so if we look here, this one is up and this one is up. Okay, and so, and then as the limit of x approaches positive infinity, which is our positive infinity to this side, our y values are going up. And so this also, for our y values, will approach also positive infinity. Okay, and then as the limit of x approaches negative infinity, so the negative, our y values are also going up, so those will be positive infinity. And so if you have a positive leading coefficient of even degree, they're going to be the same. Okay, if we have a positive leading coefficient of an odd degree, they're going to be opposite. And so here, if we look, this is down, this is negative infinity, and this is up, and this is positive infinity. Okay, so as the limit as, I didn't put that limit, as x approaches infinity, so the right side, our y values are going up, so that would be positive infinity. Okay, and then as the limit as x approaches negative infinity, so the left side, our y values are going down towards negative infinity. Okay, so positive leading coefficient, it's up, up. If it's an even degree, a positive leading coefficient, but an odd degree, it's down and up, and so these are opposite. Okay, here we have a negative leading coefficient. So that means your end behavior here is down, and it's also starting down. So it's down and down. And this is positive infinity, this is negative infinity. So a negative leading coefficient with an even degree means they're going to be the same. And so the limit as x approaches positive infinity, y approaches negative infinity. And then the limit as x approaches negative infinity, our y also approaches negative infinity. Okay, so you have to look at that end behavior. So negative infinity here, positive infinity here, so this is up, this is down. So as x approaches, so the limit as x approaches infinity, so the right side, y approaches down, so that would be negative infinity. And then as x approaches negative infinity, our y's go up, so that would be positive infinity. And so these are opposite. So negative leading coefficient, odd degree, opposite. Okay. So if we look at some examples, and so you can either look at this just by looking at your leading coefficient, you can find out all this information. or you can actually graph it. So if you look here at this leading coefficient, so it's a positive leading coefficient of odd degree. Okay, so A is this. So if it's a positive leading coefficient, so that as the limit as x approaches infinity, so x approaches infinity, our graph is going up towards, so f of x approaches positive infinity. Okay, as the limit as x approaches negative infinity, so the left side, negative infinity, our f of x approaches down, so negative infinity. So there would be our limits. Okay, so that's confusing right there, I'm sorry. You guys got it, it's fine. Okay, and so if we look at this one, two leading coefficients, positive leading coefficient with even degree, so positive and even, so that means that it's gonna be up, and they're really gonna be the same, okay? And so if you wanna do, your negative infinity, positive infinity, you can graph it. So the limit as x approaches infinity, our f of x approaches, so positive infinity, our f of x is up, and so that would be positive infinity, and then our limit as x approaches negative infinity, so the left side, this is also up, our f of x approaches infinity. Okay. And so finding the zeros of a polynomial function. So we should know how to do this. So whenever we find zeros of a polynomial function, we have to factor, or we can graph it, but let's factor. Okay, let's practice factoring. So if we can do it by factoring, if we solve it algebraically, if we have x cubed minus x squared minus 6x, first off we can factor out an x to get x squared minus x minus 6. Two numbers that multiply to get negative 6, but add to get a negative 1, or a negative 3 and a positive 2, so those go there. We can set them equal, okay? So if you notice here, our graph is a cubed function. So kind of start to get in that habit of think, okay, cubed, that means I can have up to 3 zeros, okay? And then for maxes and mins, I can have up to 2 extremas, local extremas, okay? So for 3, we have 3 zeros here. We have an x equals 0. We have an x minus 3 equals 0, so if we add 3, that would be a positive 3. And then here, if we subtract 2, we get x equals negative 2. And so if you graph it, you can see your zeros are negative 2, 0, and 3. Okay, now multiplicity of a 0. So this tells you if you have it in factored form, your multiplicity, you can see the behavior at that 0, okay? It's either gonna cross through that graph, or it's gonna bounce off of, or cross through that 0 or bounce off that 0. And it's in factored form, and so if you have this in right here in factored form, that's called your multiplicity, okay? And so if we have a polynomial of a function f of odd multiplicity, so odd multiplicity, that means it crosses through that x, x, and then if you have, and it's your 0, and then if you have a polynomial of an even multiplicity, it bounces off that 0. Bounces off the x. Okay, and so if we look at some examples, so it says to state the degree and list the zeros of the function, so it's already in factored form, so that's kind of a bonus. F of x is equal to x plus 2 cubed, and then x minus 1 squared. So we are going to state the multiplicity of each 0, and whether the graph crosses the x-axis at the corresponding x-intercepts, and then scratch it by hand, which it's already there, but that's okay, ignore that. So if we look here, so we're ignoring, we're going to look at that x plus 2 cubed and that x minus 1 squared. So here, your 0 is the x plus 2 is equal to 0, subtract 2. So here your x is equal to negative 2. So your 0 is negative 2. Okay, the multiplicity is the exponent of that factor. So the multiplicity is 3. Okay, so that means you have 3 zeros at negative 2. Okay, so at negative 2, because the multiplicity is an odd number, it crosses through that graph. So if we look at our graph at negative 2 here, if we notice, it crosses through. Okay, and then if we look at x minus 1 squared, so x minus 1 is equal to 0, add 1. Your 0 is 1. Okay, the multiplicity is 2. Okay, so your multiplicity is 2. And because 2 is an even number, it bounces off x-axis at that 0 of 1 right here. If you look, it bounces off, it doesn't cross through. Okay, and so here we have a total of 5 zeros because we have 3 negative 2's, so like our x values are negative 2, negative 2, negative 2, 1, and 1. So 1, 2, 3, 4, 5. However, you're not going to list it out 3 times. You're going to say negative 3 with a or negative 2 with a multiplicity of 3, and 1 with a multiplicity of 2. Okay, so there's that, and that's it. Okay, so you have 10 total questions in 2.3. Reach out if you have any questions. I kind of went fast, but you guys are wonderful professionals and you'll do great. Okay, cool. Bye.